Complete it up. What? Students present in online, is my voice audible? Everything is fine technically. Yes?
Yes, ma'am.
So it's been so long. Long ago, so long ago, very long ago. Last week there is no classes. Escape, right? So I think the previous week we stopped. There is I thought okay last week if there is one more classes I'll come to solid state, but our bad luck, fine okay. So today I'll complete solid state. So do you remember what all things we have read so far?
Types of voids.
Yeah. Types of voids. Types of voids. Okay. Types of crystals. AB type. In that we have seen three types. Sodium chloride, cesium chloride, and one more is zinc sulfide. Right? So in that I have taught three types. In sodium chloride, what kind of void will be present inside it? See, this is the impact of the longer always. Okay. Yes. So it's octahedral void. The coordination number will be, the range will be of 0.414 to 0.414 to 0.73. Correct me if I'm wrong, right? Yes. So I have also given many examples in the presentation, right? I don't want to get into it again. And cesium chloride having cubic void. Okay, in all the 8 corners, lattice points, there will be 8 atoms present and one big cubic void will be in the center, right? That is cesium chloride, and coordination number is 8, right? And zinc sulfide, what happens? Alternate tetrahedral voids. Okay, so the coordination number is 4 and the range will be 0.225 to 0.412. Okay, now we are getting into AB2 type. Okay, so here there is no illustrations of diagrams. There will be no illustrations of diagrams, just only the calculations. Okay, because it's not the vision is not proper. Because there it will include all the tetrahedral and octahedral voids. If you're just moving into spinal and inverse spinal, there it will be huge structure. So only the calculations. If you just take the salt, place it in a microscope, you will be seeing this kind of structure. That is what I'm going to draw. Okay. So all the last three biology. My voice is recorded there. Clear? So now we are getting into AB2 type. Okay. So far we have read AB type. Okay, in AB type, 3 types. In AB2 type, I'm going to discuss only 2 compounds, that is calcium chloride and sodium. Okay, so in this calcium chloride, this C2 plus, it will occupy all the CCP lattice. Here, I'm not going to draw the structures again and again. Okay, so next, this fluorine, it will occupy the tetrahedral voids. Okay, so when it is occupying the CCP lattice, what will be the Z effective number? What will be the Z? CCP is nothing but XTC, right? So, come on, man. What is this? 4. Yes, exactly 4. Everything like it forgot. So, see, 8 into 1 by 8, this will be present in the corner. And for space center, FCC, 6 into 1 by 3, 6 points present in the places. Remember it or not? So what happens here? It is 1 plus 3, 4. Okay, and the fluorine will be occupying in the tetrahedral voids. Okay, so it will be, what is the formula for tetrahedral void? 2 into N, that is 2 into zeta, that is 2 into 4 is equal to N. So CaF2, for calcium it is CaO and F8, that is the simple ratio Ca. Okay, tetrahedral void. Another example is calcium chloride and barium fluoride. One question. Should I ask Right here, the O2 minus will occupy the FCC. The writing itself, this doubt should be arise for, right? Okay. Or CC. So here the effective number will be 4. And for sodium, again tetrahedral bond. So 2 into N, 2 into this 4, this 8. So Na8O, that is Na2. This is the only example. Okay, for this. Yes. See, majority of the crystal lattices, the anions here are taking NaCl or cesium chloride, zinc sulfide. What happens there? The anions will come and sit in the lattice points, corners. But here you can see this fluorine is anion, but it's occupied the tetrahedral void. Why? Can you understand? Exactly, it's small size and it's highly reactive. When it is placed in the columns, what will happen? Yeah, what will happen? It will react with another neighboring cell, neighboring unit cell. So to avoid that, what happens? This fluorine is placed in the void. Okay, tetrahedral void. It is not placed in the corners. Clear? Okay. So today we can complete the solid state. Tomorrow we can go for Haber. Interesting chapter. If you are like, you should also have the coordination with me. Very beautiful chapter. Okay. So initially solid state also went like that. But see now, forgot everything. And next one is copy this thing. Shall we move on next one?
XTC or CC?
Yeah. XTC also. Okay. Yeah. So anything you can take anything. Okay. So next one is final and inverse final. Third one is final type and fourth one is inverse final type. Okay. And here someone is copying. You copied or not? Copied. Inverse final. What is the name of the compound? It's multiple oxidation states. Have you studied the redox reactions? Yes. What is this oxide? Don't say ferric oxide. Definitely don't say ferric oxide. It's a mixed oxide. Calculate the oxidation state for this compound. What's the oxidation state? Don't calculate the oxidation state.
Minus 3
Minus
by 4.
minus 3 by 4.
Just say
Minus 3 by 4. 3 by 3. See, if I need to calculate the oxidation state for iron, EX plus 4 into minus 2 is equal to 0. Minus 2 is the valence key. Okay. So 3x minus 8 is equal to 0. 3x is equal to 8. X is equal to 8. This type of oxidation state exists anywhere? Yes. This type of oxidation state exists anywhere? So how we will derive the oxidation state for this compound? Sum of which oxidation? Expand the structure means you're almost. This is a mixed oxide. Mixed oxide. What is mixed oxide? This is not possible. Okay.
Within that,
Yeah, see, this can be written as FeO plus Fe2O3. Yes or no? This is a mixed oxide. So for this the oxidation state will be plus 2. Okay, for this oxidation state will be plus 3. 3 into 2 is so 2 divided by 2 plus 3. So likewise you have to calculate the oxidation state for this kind of mixed oxide. Clear? So as such you shouldn't derive 8 by 2 because oxidation state will not arrive in fraction or in point values. Clear? You have read in your last year have you gone through the chapter? Yes. So for these two things, how the arrangement will be? See here for AB2O4, as usual, the oxygen will be occupying FCC. So it will be having ZFO4. And this A, see this will be having O2 minus B3 plus plus. These are the oxidation states. Okay, so you can ask me 2 plus, 3 plus. See, 8, 2 plus in the sense definitely the S blocks alkali earth metals can occupy this. Beryllium 2 plus, Mg2 plus. Sorry, beryllium 2 plus, Mg2 plus, beryllium, magnesium, calcium, strontium, barium. They all can come under this category. So P3 plus means boron, family cation comes under this category. Here, yes. And also the D blocks stable oxidation state categories. Magnesium, zinc. I think your D and S block is still there to keep, right? Okay. So here we will 8 2 plus. So here it will be having 1 8 of octahedral void will be occupied. Okay. So no, not octahedral void. Structure will be still it will be tetrahedral. Okay. So actually it's quite in drawing the structure, everything is not included in the syllabus. Just know this thing. So tetrahedral void here, how to calculate the tetrahedral void? 2 into n. So 1 into 8, 2 into n, 2 into 4, 8, it will be 1. Here and B 3 plus, which is nothing but half of octahedral. So half into octahedral void will be 4 as section. So O4 A1 B, this is A B2 4 times. Clear? So in this there will be tetrahedral voids will be occupying the 1/8 of the unit cell and octahedral void will be occupying 1/2, that is half of the unit cell. Okay? This is hard to draw. Okay, visualizing in Google also there will be no image. Just these kind of calculations and know the examples. The examples will be of magnesium, as I already said, Mg will be having +2, aluminum will be having +3 exactly. And another one more thing, it will be having magnesium and zinc. It will be +3 oxidation state. These are all the examples. Clear with this thing? Another one more thing, and we can go more into brackets. Clear with this thing? Yes, it will be quite confusing, right? But this kind of calculations will be. And here, as such, the oxygen will be occupying the FCC or CC. Both are same. So again, F2 plus, because iron is having +2 and +3 oxidations. Right now I show you, right? F3 plus F. See, I have written 2 F3 plus. See, this will be quite confusing. But know the calculations and just go with the examples. Okay. So for this F3, log 5, 1/4 of octahedral. Okay. So here I have written 2 Fe3 plus. Why? Because 1 Fe3 plus occupies octahedral void, 1 Fe3 plus occupies tetrahedral void. Clear? So we are applying 1/4 of octahedral void. If we are applying 1/8 of tetrahedral. So everything will be of 1/4, 4, 1, 1/4, here also 4, 1, 1/4 is 3. Clear? 2 into n, so it will be. So just see Fe3 plus Fe2 plus 4 to 9. So Fe3 plus we have 1 center. For Fe2 plus we have 2 center. Right? And for O so totally Fe is 3, iron is 3, oxygen is 4. Fe3O. Clear? Clear with this one? Okay. See, just remember there is 4 types of crystal structures. First one is AB type, AB2 type, and third one is spiral, and fourth one is inverse spiral. In AB there is 3 types: NaCl, CaCl, and zinc sulfide. And second one in AB2 type, I have said about calcium chloride and sodium. And in spiral, I have read about A. This A can be of anything that belongs to alkali earth metal. This B can be of anything that belongs to boron family as well as the stable oxidation states representing D block element. So that's why formally I have written this. And oxygen. This inverted spiral will be applied only for mixed oxygen. So this will be applied for another example will be Pb3O4. elementary, and that comes the use of the crystal structure. Now we can go for Bragg's law. Yes, shall I rub this thing? Shall we move? Now, we're getting to Bragg's law. Anywhere, at any point, have you heard about Bragg's law? The main equation, anywhere? Okay. So what is Bragg's law? Doesn't keep your mind. See, Bragg actually, he is a scientist. What he said, this solid crystal, the particle arrangement will be in a proper way. That we know. The solid crystal, the particle arrangement will be close and it will be arranged in a proper way. Right? It will be arranged in this way. Correct? The particles will be arranged in this way, right? Okay. Now, first initial point, the particles are arranged in a proper way. If when I'm passing an X-ray on this particle, what happens? Okay, it gets deviated. Okay, so what happens? It will be getting deviated. Correct? Okay. Okay. Name this ray as X. So this is an X-ray. Name this ray as Y. Now I'm letting another one more ray here. Again, there will be a deviation will be happening. Okay. So which one will cover longer distance? Which one will be having shorter distance? No, why you should observe? See, here the X-ray is coming, here also the electrons will be there. Here also the electrons will be there. Initially, what happened? The reflection will be happen, deviation will be happen. Correct? Right? See, the absorption will be there, but the majority will be only deviations will be there. Here also electrons will be there. Here also the electrons will be present. Immediately, what happened? The deviation will be there. Alpha scattering experiment in your atomic structure. What it says? So, alpha scattering experiment in your atomic rays. It will be deviated. In gold foil, they will be keeping like this. What happened? It will be getting deviated. So, what happened? Majority of the spots will be seen here and here. Okay, only less spots will be seen directly. Of course, the nucleus, the electrons will observe, but the majority, what happened? Only the deviation will be happening. Clear? So, what happened? It will be getting deviated. Which one will be having longer distance? Say, name this as Y. This is Z. Which one will be having longer distance? Z. Exactly, you're right. Why Z will be having longer distance? Can you understand my question? So you're all sleeping. No. See, this is penetrating inside crystal lattice, right? So obviously it will be having a longer distance, right? Okay. So this is on the top of the layer. This is on the surface. So this will be having a shorter distance. This is penetrating inside the layer, crystal lattice. It will be having a longer distance. Let's suppose if I'm passing another ray, so just come back. It will be having still a longer distance. Sorry? Okay. Because all the particles will be what happened? All the particles, electrons will be getting repelled. The force that will be getting more, the force that will be getting traveled will be longer. Trying to explain it. Okay, fine. Okay, don't stop it. So what happens? There will be more amount of particles will be there. When the penetration is happening, all the particles will be getting repelled. So it will be traveling longer. But when it's coming to first layer, there is only one particle. Surrounding there will be two particles. Less repulsion will be there. It will be traveling to this. But by the penetration, so much of particles will be there. So it will be traveling to longer distance. This is what Bragg's law. Okay, clear. So here, this will be ambient T type. Can be represented as ambient T deviation. Clear?
You are saying about repulsion, right? So there can also be attraction,
Attraction will be okay. Complete.
which prevents the rays from covering long distance. So
Why? What happened? Okay. Okay. That can be. You're saying that there will be attraction also. Yes, but what I say, attraction will be there, but it will be very, very less. The nucleus will be only inside the particles, right? If this is the particle, there will be inside the particles, one nucleus. Attraction will be there, but it will be very, very less. Comparatively, the repulsion will be very, very more. The electrons is a fast moving particle. It will come again on the particles. The valence electrons will be there. It will hit and it will immediately it will repel. Okay, so when it is penetrating, there will be more amount of particles will be there. Longer the distance, it will deviate. Clear? Clear about Bragg's law? From this thing, he said an equation. What is that equation? That equation is n lambda is equal to 2d sine theta. Clear? This is the equation. There is actually there is no elaborate derivation of how it comes. Okay, so in your syllabus, this is the main thing. Here, this n is nothing but number of radiations. So here, how many number of radiations? 3. 1, 2, 3. Okay, this is number of radiations. Clear of this diagram? You understand what Bragg's law speaks about? E rays. E rays. Okay. See, your rays depends upon the force. There is many rays are present. Okay, but some rays are harmful. Okay, some rays, if you're just taking X-rays, it's quite harmful. Okay, so if you're just taking alpha rays, beta rays, IR rays, UV rays, depends upon the fastest moving thing, frequency and wavelength. Okay.
Ma'am, can you repeat what is N?
So this n is nothing but your number of radiations. What is this lambda? This is the length of the wavelength. This is your wavelength. Here, this is your wavelength. This d is nothing but I've shown this thing right. This is the distance between these two layers. Here, this is the d distance. And this theta is nothing but your angle of deviation. This was Bragg's. Okay. Or you're trying some problem. Bragg's law. With this formula. You're saying about the incident and so I think that thing is not analyzed here. Here we have doesn't compare this angle of incident as well as deviation point. We doesn't compare. Only thing is getting deviated. That's it. We have doesn't get into like whether it's both the lines are equal or not. We have doesn't evaluate it. Okay. Now solve the problem. This d is the distance between these two parallel lines. Clear? Right. So now, come on, solve this problem. An X-ray have wavelength 70.93 is deviated by angle 2 theta equal to 14.6. This is second order reflection. Find the distance between particles of wavelengths. See, this is a formula. N lambda is equal to 2d sine theta is your formula, right? So, from this, what are the values they have given? Lambda here they have given 2 theta. You'll be getting confused. 2 theta is nothing but actually most of the problems they will give only as 2 theta. Why 2 theta in a sense? See what happens, they have been taking both the thetas. Okay, so just summing it up, 2 theta. So what happened, you have to take it as theta is equal to 14 points, theta is equal to 7.3. Okay. And in your question, they will be giving sin 7.33 value is equal to 0.120. Now listen easier. Calculate. See the second order reflection is nothing but your n is equal to 2. So then I can ask you this. So d is equal to n into lambda divided by 2 sin. So actually here the answer is in meter. So 70.93 into 10 to the power minus 1, convert it into meter. So it will be like 2 into 70.93 into 10 to the power minus divided by 2 into sin theta is 0.1. Just make the calculations and see. What's your answer? Very fast. Yeah, say to convert it into meter, right? See here I have written into 10 to the power minus 5. Clear? What's your answer? 53.1 into 10 to the power minus 11. See, 3.1 into 10 to the power minus 7. Why is 10 to the power minus 7?
No, 0.56 into 10 to the power minus 9.
Make it as 5.60 order. 5.60 to 10 to the power minus 10. That's the answer. So wait. Till this step you are right. Right? So maybe this two will be taken care, right? So automatically. So your answer will be 5.62 into 10 to the power minus 6. Okay. Yes. Shall we move to the next topic? Everyone got this answer or not? Only one. What about the rest? Got. Huh? No, it's right. Shall we move on next one? This much for calculation. Take it in your home. Okay, this is the answer. Okay. So now we are moving into imperfection in solids. What is imperfection? Okay. You have studied about atomic structure. Okay. In atomic structure, what Niels Bohr said about the atom. How his prediction towards atom. Hey, positive charge and then negative charge, that is universal thing. I said, what is this kind of prediction? See, it's fixed. What he said means there is nucleus, and what happens? The electrons will be revolving around its orbit or in its shell in a fixed path, fixed trajectories. Okay, fixed in the sense if the electron is moving in this way, it will be only moving in this way. This is what Niels Bohr said. But after that, another scientist came. His name is De Broglie dual nature. He said there is dual nature of matter. That's after that, another one more man came. That is Heisenberg. He contradicted Niels Bohr point. What? How? Uncertainty. What is uncertainty?
Displacement and
I don't want in terms of anything like your book. What is in their book? I don't want it.
things can be
Momentum and I don't want this momentum. See, Niels Bohr said the electron is revolving around in a fixed path. But what Heisenberg said, no, it is not revolving in a fixed path. Everything in this world is uncertain. Likewise, the electron is also uncertain, which means if any external force is just like hitting on the electron, what happens? See, I am the electron. If someone pushes me, what happens? I'll go front and again I'll be standing there. Likewise, the electron also, if any external, say for example, if X is hitting on the electron, what happens? It will move a little farther and again it will make that revolution. Okay, see, there is nothing called shells, there is nothing called orbits. The electron will keep on revolving. It makes the shells and orbits. Clear? So that's how nothing in this world is like uncertain. Like, we humans are also not uncertain. Right? Even we will be having a deadline, right? So likewise, this crystal connect that thing. This crystal structure, I'm saying it's a perfect three-dimensional arrangement. It's not perfect. That's an imperfection. Of course, there is an imperfection. Okay, you're eating your sodium chloride salt. So in your sodium chloride salt, definitely accurately all the edges there will be Na plus ions will be located. No, there will be an impurities of Mg2 plus. Correct? Mg2 plus impurities. Correct? In 10 kilos, there will be 2% of impurities can be there. Can't be avoided. That is how we are going to deal with this imperfection. Okay. No solid will be perfect unless it is present in 0 Kelvin. What is 0 Kelvin? That is 0 degree temperature. Exactly. So if you are heating, you are externally heating. If your temperature is getting rise, definitely your arrangement, your crystal arrangement, your solid crystal will also be getting changed. So there arise your imperfection. Clear? See, definitely your sodium chloride salt is there. When you are dropping into your sambar or rasam or curry, what happens? The arrangement will be getting distorted, right? Clear? So there the imperfections arises, right? So likewise, the imperfection will be there in each and every crystal structure. Okay, so this imperfection will be of different types. See, this is my structure. I'm explaining you in this crystal mix. Okay, this is just a unit cell. Okay, so here I can't say exactly all 8 lattice points will be situated. Like one lattice point can. So this is imperfect, right? So this is 8 lattice points in a unit cell. Just imagine a big crystal lattice. Out of a big crystal lattice, this only one imperfection is negligible. Okay, it is negligible, but still it's an imperfection. Correct? So that is we are going to deal. There is different types of imperfections out there. So what is the proper definition? In your book, there will be many definitions will be there. Okay. Second one is atomic effect or point effect. Third one is electronic. Okay. What is line? Entire line or entire row will be getting CCP enclosed cubic packing A, B, C. We have seen three layers. You remember or not? So in this three layers, complete one layer, remove completely one layer. So that entire layer is getting disturbed. That is your line. Okay. So actually, you people don't need that much on line because removing the entire rows like not is not that much easy. Only in rare cases it will happen. So example like in CCP. Now in atomic and point effects and in electronic effects only you will keep it more number of. Okay. So second type is atomic and point. That is nothing but any one point or any one atom. Okay, there the imperfections will be arised. Okay, atomic in the sense any atom. Point means that is points. Clear? So second one is atomic defect or point. This atomic defect or point defect is divided into three. Okay. First one is stoichiometric. Second one is impurity. Third one is non-stoichiometric. What is stoichiometric effect? What is stoichiometric ratio? What is stoichiometric ratio? It's a simple ratio. Correct? C6H6, which means 1:1 ratio. CO2, 1:2 ratio. H2O2, 1:2. It's a simple ratio. Okay. So when the imperfection is arising in any crystal lattice, the stoichiometric ratio should be getting disturbed. Okay. So how in the sense, say for example, okay, if I'm having metal, okay, cation, anything, you can say this is a particle. Okay. If any one particle is removed in this sense, definitely there will be a point of stoichiometric. We just keep it as cation, anion, cation, anion, cation. Like this. Okay. So what will be the ratio right now? There is 1, 2, 3, 4, 5, 6, 7, 8 cations are present. So cation is 8. 8 anions are present. Anions are 8. So now the stoichiometry is 1:1. Okay. Suppose if this anion is getting removed, what will be the stoichiometric ratio? Is that a proper stoichiometric ratio? No, it's not proper stoichiometric ratio, right? So this stoichiometric effect is, suppose you know what happened, there will be some anion or cation will be getting out or just will be occupying the interstitial. But still its stoichiometric ratio should not be getting disturbed. Okay, this ratio should be properly maintained. That is stoichiometric. So here,
Disturb only will be negative effect.
see, it's not wait. This anion, okay, can go and sit here. The stoichiometry is same, but the arrangement is getting deferred likewise. Okay, no issues. So if this anion is getting out, so what happens? The anion is there. So what happened to maintain the stoichiometric ratio or to maintain the electrical neutrality? The cation will also get removed. So C7 is like cation 7, anion like somehow it may be getting balanced. Okay. So here in this stoichiometric effect, it happens in both non-ionic compounds as well as ionic compounds. Okay. Wait up. No. What happened? I got you. What happened? Nothing. Tied up. Okay. Yes. Is it going up? No. Going up. No. No. Sure. Going up. What shall we do? This is in your chemistry. This is in your 12th standard. Somehow you need to study it. You can't skip it, right? Yes. I'm trying to make it interesting, but I don't know how. Yes. So in this stoichiometric ratio, there is it is occurring in two things, that is in ionic compounds, in non-ionic compounds. Okay. So in ionic compounds, you have Frenkel defects and Schottky defects. And in non-ionic compound, you will be having vacancy defect and interstitial defect. Okay. So this vacancy defect and interstitial defect, here what happens? The particles will be arranged in this manner. Okay. Any one of the atom will be getting vacant. Okay. So what happens? The ratio will be getting imbalanced. So another one more thing also. Likewise, what happens? The vacancy. Okay. Any one of the atom or any of two of the atom, there will be vacant spaces with it. This is vacancy defect. What is interstitial defect?
Atom need to
Exactly. So interstitial defect means this is a proper arrangement in small void. In interstitial spaces, what happens? The atom will come and sit. Okay. This is interstitial. Okay. Can you able to follow? Yes. So now shall we move to Frenkel and Schottky defect? Shall we move to Frenkel and Schottky? Okay, fine. Keep your pen down. After copying, keep your pen. I'll only talk it. I'll not talk it. I'm going to ask some of the interesting questions. Fine. Take the sodium. My questions. Sodium, when it is present as a sodium form, in atomic form, you are saying it highly reactive. But when this sodium is present in sodium chloride, what happens? It is getting in. It's not like it's not that much reactive. What is the reason?
Always condensates. It needs for the electron already chloride.
Okay, because it's attaining the stablest form. Okay. Now, okay, leave that. Why? Next topic is haloalkenes and haloalkenes. Okay. Why? What is the purpose for studying haloalkenes and haloalkenes? Organic chemistry is everything made up
So
of.
we should know the topic.
Why? See, for 11th, 12th, majority of the portions will be connected to your day-to-day life. That's why you're studying 11th and 12th, which is a basic for your entire life. Till your last breath. Why you're saying 11th and 12th is important means it will connect to everything. Why you're studying solid state? Because you're surrounded by solid, man. Correct? Everything is solid. You have to know the properties. Okay, so that's why. So why are you studying haloalkenes and haloalkenes? Used in industries. If it is used in industries, then why you should study? In medicines. Okay, you're all taking paracetamol. Okay, you are all taking anesthesias. Do you know this name? Chloroquine, chloramphenicol, chloroform. They're all your haloalkenes and halogens. Okay, so why you are studying this thing is because you are taking medicines, right? You are all studying your 11th and 12th. I don't know whether how far you are just like deeply getting into it. If you are properly studying this haloalkenes and haloalkenes, you will know how this chloroform is getting prepared. How this chloroform is getting prepared. This CH4 and Cl. CH4 is nothing but your hydrocarbon. Why are you studying hydrocarbon? No, day-to-day life, pharmacies is not. Hydrocarbons is nothing but fuels for petrol, diesel, LPG, CNG, liquefied petroleum gas, compressed natural gas, daily or eating, no. The gas, ethane, butane, propane, everything is hydrocarbon. Okay, likewise also, this haloalkenes and haloalkenes, majority of the compound, no, paracetamol, chloroform, general anesthesia, thyroxine, that is a important tablet for you. Not now, it is going to be used after your 30s. Definitely there will be a hormonal imbalance will be there, because generally after the age of 30 our body will be having a kind of transformation. At that time the hormonal imbalance will arise, so you will be having a tablet, this thyroid and goiter disease, everything will be coming. So at that time thyroxine hormone to balance that thing, you will be taking a tablet, that is the halogen. Okay, so everywhere in the form of medicine, you're just taking halogens and halogens that we are going to see tomorrow. Clear? Each and every chapter has its own value till your last. Okay. Try to see when you're just taking this paracetamol, how do you just likewise you have the if you're having the interest towards it. Knowledge is different from wisdom. What is knowledge? What is wisdom? Who knows? Knowledge is? Yeah, come on. Knowledge is? Knowledge is? See, knowledge is, say for example, you are inferring something else and for 1 year it will be there in your mind. Wisdom in the sense that is application, telling the, which means like you're having the kind of, clarity towards the subject. That is wisdom. That is going to help you, whether if you're going to competitive level, whatever level, till your last breath, you need to remember all these things. Clear? Fine. Let's move into this critical defects. So tomorrow, modern explanation. Next one is Frenkel defect and short-lived. Come on, I'll make it a little bit fast so that I can complete it. See, today you're just going to get your assignment or something. Okay. So this Frenkel defect and short-lived defect. See, in this Frenkel defect, what happens? Your cation and anion will be having that is, your anion will be having a large size, and your cation will be having a smaller size. So here, what happens? In your textbook, there will be more examples will be there have been mentioned. You can go through all the examples. Go through all the okay, like this. Maybe like any layers are just are not right. So what happens in this Frenkel defect? This one of the cation, it will go and sit in some other interstitial space like this. Okay. So what happens here? The hole or the void will be here. So this kind of thing is fragmented. Okay. So if this is happening in the sense, what happens to stoichiometric ratio? Nothing. Just a cation is just going and sitting here, right? So your stoichiometric ratio will not be getting affected. Your density will not be same exactly. The stability. Yeah, your stability will be getting disturbed, and your coordination number will be getting low, because see at some point if you're just taking here, in this point what happened? Your coordination number will be. I'm taking here one anion. Okay, I'm taking here one cation. See here, there is a void is this. See, you actually there is no. You just need to know about there is no fixed numbers. Comparatively, we having low coordination, but that's it at this point. Because not only this cation, there will be number of cations will be moving. Number of anion can also be getting moved. So what happens? It will change its position, but it will be only the crystal lattice. Stoichiometric ratio will be balanced, density will be there, and the stability will only be getting this. Clear? So what happens? What is the question I asked?
Coordination number.
It will be low. Okay. So this is Frenkel defect. One of the cation will move and sit in any other interstitial space. Clear? What is short-lived?
Frenkel defect will be same as interstitial defect.
But in interstitial defect, we will be non-taking. Interstitial defect and vacancy defect, I said about non-ionic compounds. They the atoms. But here what happens? Anion and cations. Okay, I'm comparing. Here. And in short-lived defect, what happens? Here, this anion and cation will be having a similar size. Both of them will be comparatively having similar size. So initially, what happened? It will be like this. Correct. So what happens? This one cation will be getting out of the crystal lattice. Okay. So what happens now? The stoichiometric ratio will be getting disturbed. Clear? So now what happens to the density? It decreases. What happens to the stability? It decreases. What happens to the volume? It will remain same. Volume remains same. Okay, there is so much of particles will be arranged. Okay. So much of particles. If I'm removing two particles, similar length, width and height will be same, right? Clear? If I'm removing two particles or 2 points, there will be no change in its volume, right? Only its density, that is the mass by volume will be getting disturbed. Stability will be getting disturbed, but the volume will remain same. Clear with this thing? One more point. See, there is two vacancies of this. Void is present. So what happens? This anion will jump here. This cation will jump here. So what happens? The electrons, the particles will be freely moving. So the conductivity increases. Clear? Clear in Schottky effect? Yes. And now next one, we are getting into impurity defect. Second one. In atomic or point defect, we have seen three. Correct? Stoichiometric, impurity and non-stoichiometric. In stoichiometric, for non-ionic and ionic, we have seen 4 kinds. For non-ionic, vacancy, interstitial, and ionic, parental and short. Now we are getting into the atomic point, second type, that is impurity. Okay. There is many examples for parental defects, AGCL, AGBR, AGI, ZS, that's all in your text. Okay, you can go through it. Now, next one, impurity. See, compare the density, stoichiometric ratio, stability. See here, this will be having higher coordination. Okay, of course, every 2 or 3 months will be there. This will be having higher coordination. So, compare all these kinds of things. Okay, but the volume will not be getting this. Okay, there is like one big box is there. Like small balls is there. You are taking one ball, there will be no disturbance. Volume will be there, the length will be there, width will be there, the height will be there. Volume will be not getting altered. Now we are getting into impurity defects. So it will be taking place in a 2 solids, that is covalent as well as an ionic solid. See, generally impurity refers as, so have you studied metallurgy? Isolation of elements. So isolation of elements, you are going to deal in your 12th standard. Okay. So there you will be reading a word. There will be many words like carbs, slag, rock, they are all the impurities in the sense. In periodic table, there are many elements, right? Iron, Pb, lead, nickel, all that elements are not present as a pure form. Okay, you will be taking from any earth crust or something else. You will be enrolling it in any purification forms like hydraulic washing, fourth flotation process. So likewise, finally only your purest metal will be obtained. Okay, I'm not speaking about that kind of impurity. Here the impurity defects will be dealing about any other cation can come and say. Sodium is there, cesium can come and say. Magnesium can come and occupy. Likewise, here the impurity, one metal can replace by another metal. That is nothing but doping. What is doping?
Replacing.
Doping. Okay, semiconductors. Have you gone through the chapter semiconductors? No. The first one is with covalent solids. Okay. So in covalent solids, here I have taken an example of silicon. Okay. So here, silicon, germanium, they are all semiconductors. Okay. So the silicon are all arranged in this. Okay. So what happened here when you are just doping the sense you are mixing it with an impurity. Okay. So when you are just getting doped, what happened? This silica is a group 13 or 14th element. Group 14th element. 13, group 13 is boron family. Group 14 is carbon family. Carbon, silicon, germanium, clear. So group 14th element, when you're just doping it with group 15th element, what happens? So there in group 15, arsenic is a semiconductor, right? So when defect. Okay, if I'm taking Na plus Cl minus. This is an ionic solid, right? Everyone is sleeping here. He is dying and sleeping here. Right? They so hectic in your school. Compared to last class, is quite better. You take so energetic. So when you are just doping it with, always when you are just doping, you have to take the next group elements. Okay. See, if I'm taking silicon, group 13, silicon is group 14, I have taken group 15 aristic element. So likewise, here I have taken sodium as group 1. So you have to dope it with group 2, that is strontium. Okay. So I'm taking strontium 2. Okay. So what happens in any one of the places of sodium? Okay, what happens? The strontium will come and sit, right? It will be having 2 plus of its charge. But if you're just looking into it, here the cation will be more because the cation left is Na plus, which is having 1 charge. But here, strontium 2 plus, what happened? Excess 1 more charge cation is present. So in order to maintain the electrical neutrality, 1 more cation will also be moving. So this is your ionic solid. Clear with this thing? Maintain the charge. Another?
Next group element.
Ah.
So is there any rule that we need to take only that group? We need to take one particular element or we can take element of that?
You are saying is there for doping? Is there any fixed
element for element or we can take any?
Okay.
Why are you taking only strontium? Why not take it?
See, you can take beryllium, you can take lead, you can take strontium, but group 1 and group 2. Only nearby elements should be taken. Okay. So likewise it is there. Okay. So actually doping in the sense you will be taking the neighboring groups elements. There is no particular thing for elements, but you should not take group 1 and groups. Likewise, you should. Okay. So clear? To maintain the charge, what happened? Another 1 more sodium cation also will be. So this is your ionic solid. Clear? Now what happened? Your electrical neutrality also getting maintained according in terms of charge wise. Now shall we move to non-stoichiometric effect? In this non-stoichiometric effect, what happens? Your chemical formula will be getting disturbed. Stoichiometry in the sense your ratio will be same, but here your ratio will be getting disturbed. See, say for example, hypothetically, I am taking any compound, zinc oxide. If I am taking zinc oxide, okay. If I am heating, so now initially it is present in 1:1 ratio. If I am heating, definitely the oxygen will be going out of this compound, right? So exactly there will be only 1:1 ratio will be there after heating. No, definitely what happens? This will be getting reduced. So it will be like Z10, 1, 0.8 or something. So from stoichiometry to here it came to non-stoichiometry. Okay, so this is the thing we are going to do. So this non-stoichiometric effect is of 2 types. One is metal excess defect, another one is metal deficiency. So metal excess defect and metal deficiency. Non-stoichiometric. These are all there in your text. Okay. We are actually studying solid states for more than 1 month. Metal deficiency, metal excess, and metal deficiency. See, in this metal excess defect, there is 2 types. First one is by the deficiency of anion. Okay. B is by the excess of cation. From this itself, you can identify what will be happening? The cation will occupy assets to interstitials. So definitely your metal should be present in it. Okay, so your metals will be generally of cations or anions. Cations. So automatically what you will be getting? Anions. So that is what happens. First you have to remove the anion. Then you have to what happened to compensate, and to nullify you have to bring the metal. Clear? So now I will be explaining it then. Wait, I'm doing the example now. Okay, so shall I rub this thing? See, I'm taking here, I'm taking the general metal. So here there is metal ion. Okay. Now listen carefully. Your doubts will be getting clarified. See here, I am removing my anion. So here automatically your depletion of anion arises. Okay, what is the initial ratio? Okay. Now what is the ratio? Clear? So this happens. So now what the next phase is, see, this is a wall. Clear? But in any solid, okay, when you're just making, when you're removing the atom, when you're placing the atom in interstitial space, you have to note the electrical neutrality. Okay, that is very, very important. To maintain electrical neutrality is highly important in a crystal lab. So here what happens, an anion. Okay, so what happens? 8 minus 7 is equal to 1. Okay, so totally 8 cations and 7 anions. See, this anion, when it is leaving the crystal lattice, what happens? It leaves one electron. Here, so leave one electron. So minus 1 neutral. For electrical neutrality is maintained. Clear this thing? Clear with this one? No? Yes. So what happened? Your deficiency of anion occurs, but still say for example, chlorine is there. Okay, I'll explain another. See, this electron will be there. No, this is known as F center or Fabry center. Generally, in metal, in ionic solids like in this metal categories, what happens? This free electrons is responsible for imparting colors. In S-block elements, you have studied sodium, the potassium, strontium. They are all imparting colors. They are all because of free electrons. Okay, see, I'll explain.
Okay, get excited to higher even.
When you are just heating. No, wait, I'll say. See, it will be like Na plus Cl minus Na plus Cl. Correct? Okay. Now what happens? I'm heating. So when I'm just passing the sodium vapors over. Okay. I'm passing the sodium vapors over. Okay. See, the sodium is present in the atomic probability. It has totally how many electrons will be present? 11. Okay. So what happens? It will approach this chlorine. Okay. So it has 11 electrons. So definitely what happens is chlorine is already rich. It is present as Cl minus. So definitely what happens? If you leave one electron and this becomes NaCl, okay, it becomes sodium chloride, and what happens? This electron will be there. Further on heating, your sodium chloride salt will be having yellow color because of the electron. Clear? Likewise, your lithium will be having pink color. What is the green grade? Vincent grade, the strontium grade, apple grade, everything only because of this. You can ask now, you're getting the sodium. There So fluorine can leave its electron in the void and it can just come out of the cell. Clear? So this is how what happens. The entire, in your S block, the color that will be happening. So further what happens, the electron will be there, will be meeting. So what happens, it will absorb all the energy, it will go to the excited state, it will release all the extra energy. That releasing extra energy will be in your form of visible radiation that will be fills your violet beam. Clear? Clear with this thing? So this is your studying under metal effect. Now we have completed only point A. Still point B is there. Efficiency of anion, how this color is. Point B, by the excess of cation in the interstitial space. So what happens here? This is cation, anion, like this. But I have taken like this. So definitely after taking your anion, electron will be there, right? Okay. This is very angular. Wait. Okay. So what happens? Your metal will come and occupy the interstitials. Clear? So this is the metal excess. But I have one more question. My metal is occupying all these interstitial space. How the electrical neutrality will be maintained? Electron will be cation will be higher than charge will be more. Positive charge will be more. So negative charge will be removed. Negative charge will be removed. What I have said there? I have made it electrical neutrality. You have seen -1 + 1 have got it. See, if I hypothetically, can you understand my question? Can you understand my question?
That it leaves an electron.
Wait. Now, I am heating zinc oxide. We getting zinc oxide. And now I am drawing the picture. Electrical neutrality is maintaining the charge. Okay. Likewise, it's there. Now, see, the zinc 2 plus is present here. Okay, another zinc 2 plus is present. But if you're just taking the cation will be more, the anion will be less. How to maintain it? Okay. So when you're heating the zinc oxide, when you're just passing the zinc oxide, it's definitely 2 plus and O2 minus. Okay. Okay. So what happens? This 2 zinc plus will go on 6. Clear? Okay. So this O2 minus, there will be 2 O2 minus will be present. Clear? So this oxygen and this oxygen combine and this oxygen gas will be gone out. And this charge is what happened? 2 plus 2, 4 electrons will be there. Clear? 4 electrons will be there, yes or no? Okay. So this zinc 2 plus and zinc 2 plus. So here what happens? All the 4 electrons will occupy all the interstitial space and now your electrical neutrality is made. Here also 4 electrons. Here also 4 electrons. Maintain. Okay. So this plus 4 and -4 it will be getting cancelled and electrical neutrality is getting. Clear? This is your metal excess effect. Clear? Huh? Okay. See, what happened? See, in crystal, zinc cation and oxygen anion is arranged. Okay. So what happened? The zinc 2 plus is present in excess. Clear? So when you're just passing over this zinc, when you're heating the zinc
oxide gas.
Yeah, zinc oxide gas. There we have passed the sodium vapors. Right? Clear. Clear at this point. Now shall we move to metal deficiency defect and two more topics. In metal deficiency defect, clear up this thing. So there are many examples there. Examples zinc oxide. So it will be in your textbook. Just understand the concept. And now next one we are getting into metal deficiency. So in metal deficiency defect, here actually we are dealing with a metal with different oxidation states. Okay, so copper it will be having an oxidation state of +1 and +2. You know this thing? So no. Iron stable oxidation state +12. +1 out. Iron do not have +1 oxidation.
Yes,
+3,
yes.
+2 and +3. Okay, for manganese +4 and +5. Stable. This state is stable oxidation. Have you completed this thing? Okay, D and F you will be studying. Okay, no. For vanadium it will be +4 and +5. Okay. Now if I'm taking ferric oxide, I'm taking the ferric oxide. So this ferric oxide is arranged in crystal hydroxide. P2 plus and O2 plus. P2 plus. Likewise, it is arranged. Your ferric oxide is arranged in this. We know that iron also has the oxidation state. Correct? Because it's having multiple oxidation states. Both +2 and +3 is also stable. Correct? So now what happened? I'm removing. Okay. Here, I'm removing all the three atoms. Okay. So this place can be replaced by iron plus. Clear? So initially, your Fe means this Fe is also 8, this oxygen is also 8. Clear? Now we have taken three Fe2 plus atoms. Okay, it is just having a +6 plus charge, but we maintain the electrical neutrality by adding Fe3 plus and Fe3 plus, which is +6 charge, but there is a void is there. But only now count number of iron atoms 1, 2, 3, 4, 5, 6, 7, and your oxygen atom is 8. Nothing but a non-stoichiometric effect and your metal. Got the point? We have balanced by replacing the variable oxygen. Okay, we have maintained the electrical neutrality. But the void is there. It is there. Clear? Got my point? Now moving to the electrical. Okay. To all the solid, crystals or anything like, the sheet or the stone, every solid particles contain electricity. Yes.
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 Absolutely.
Everything conduct electricity. This wall conduct electricity. Huh? No. So actually, based on the electrical property, the solid is divided into three types. One is conductors, second one is semiconductors, and third one is insulators. Insulators which do not conduct electricity. This wall is an insulator which do not conduct electricity. Okay. What are the example of conductors?
Metals.
Huh?
Metals.
Metals. The metal wire. Okay, metals. Okay. Semiconductors.
Actually,
Huh?
German.
German. Same conducting. Day to day, like your TV remote, your AC remote, your diode, where it will be. See, your TV remote, you are operating from here. There is some amount of electricity is there. It is a semiconductor because it is not a very good conductor of electricity, but it is a conductor of electricity. Of course, there is base is also there, but electricity is also there, right? Based on the electrical properties, they have divided into conductor, semiconductor, and insulator. So this conductor will be having a very good conductor, like their efficiency will be very good in terms of electricity. Say for example, metals. You can take wires like gold wire, silver wire, iron wire. They are all a very good conductor. Semiconductors, diodes. Okay, so they'll be having a range. For conductors, it will be having a range of 10 to the power 4 to 10 to the power 7 ohm inverse millimeters. This is for conductors. They are a very good conductor. And for semiconductors, it will be 10 to the power 6 to 10 to the power minus 4. Okay, and for insulators, 10 to the power minus 20 to 10 to the power minus 4. Actually, they don't conduct electricity. They are very bad conductors. So, in this type, these conductors are divided into two types. Okay, one is ionic conductors, and one is metallic conductors. So, already I have discussed ionic conductors. Generally, in ionic solids, what are the constituent particles? The rings, cations, and anions. So, if the temperature is increasing, what happens to the conductivity? It will be automatically increasing. In metallic conductors, in metallic solids, what will be a constituent particle? It will be metal atoms. Atoms. Okay, if the temperature increasing, the conductivity will be increasing. Further, if you are increasing the temperature, what happens to the conductivity? Collapse. It will collapse. What happens? Bond will break. Oval and bond will. Saying about metallic, not saying oval and. I have taught you in my first class. What happened? You are saying collapse, that is right. See, if you are increasing the temperature, what happens? This metallic solids will be having a sea of electrons, right? So initially what happened? When you are just heating, the electron will tend to move faster, and the kernel, okay, when still it's observing the heat, there will be the movement of kernel will be there. So if two kernels comes close together, what happens? Immediate repulsion will happen, and the entire structure will be getting collapsed, and the stability will be getting distorted. So further, if you just keep on increasing the temperature, what happens to metallic conductors? Conductivity decreases. Okay, I taught you right. Yes, I taught you. You people forgot. What can I do for it? Okay, fine. So these conductors are of two types. This is the one I'm just trying to say. That is ionic conductors and metallic conductors. Ionic conductors, they have the constituent particles of both cation and anion. Here the constituent particle will be atoms. Just compare the temperature and conductivity. Now we are getting into the band theory. What is band theory? What is band theory? Band, B-A-N-D, band theory. Too much of pressure in your system. Here also you are waiting. Okay. Try to be more interactive. So this band theory, actually why we are studying band theory in solid state? This band theory used to identify which solid is conductor, which solid is semiconductor, which solid is insulator. For that one we are going to study band theory. Clear? Now, when reading any other phosphorus, we having atomic number of 1s2, 2s2, then 4s2, 3p6, 3d3. So there will be MD3D orbital will be there. First in electronic configuration, 4s. Okay. But in terms of orbital, first, second, third. Here 1s, here 2s, 2p, here 3s, 3d, 3d. Correct? This will be there. Now, band theory works on this. Balance check. No, not only band theory. In this point, the entire theory will only work. Any theory that will be work on this balance check. Why? Why? Because they are the one to participate in bonding. There will be the free electrons will be there. Here, you're completely filled. They are inert. They are not reactive. Right? So here we can be. So here only our band theory is going. See here, PS2, 3P3, 3D0. This valence can be divided into two types. That is electron present, electron absent. Okay. So in electron present, 3s2 and 3p3 will be there. Electron absent, 3d0. Clear? So this orbitals will be closer to the nucleus or farther to closer to the nucleus. How? Why?
It's orbital.
Because it's orbitals and because the electrons are present here, right? The nucleus will tend to attract the electrons, right? So these two orbitals will be closer to the nucleus. So they will be always having the lower side. That is, they will be always having the inner side towards. What happens to this one? It will be quite farther. Comparatively, it will be quite farther. It will be placed above the nucleus. Okay. So this will be placed closer to the nucleus. This will be placed above. That is farther to the nucleus. So in terms of band theory diagram, I can draw this thing. This is your energy. Will be getting increased, and here your 3s and 3p is present. 3s and 3p. Here your 3d is present. Okay. So definitely here the electrons. How many electrons are present here? We have taken 5 electrons, right? In terms of phosphorus. So all the electrons, what happens? It will combine together. Okay. So it will combine together. It will form a new band. That is known as valence band. So this band is known as valence band. Clear? So here what happens? There is no electron. Okay. But still, if any electrons are coming from any electrons, like from outermost shell, not from outermost shell, from the nearest atom, if any electrons are coming towards this 3D means definitely it can accommodate, right? It can accommodate because it is having an empty orbital, correct? So it can accommodate. So here what happens? The free electron can accommodate and see. Here the electrons can accommodate. But here there is 5 electrons. If there is 1 electron is accommodated here, this electron's movement will be very, very fast and its conductivity also move. So this band is known as conduction band. Clear? Because this is free. This is having more number of space to accommodate the new electrons. So this is known as conduction band. This is known as valence band in terms of your what theory you are reading? Band theory. And the gap between this two, this conduction band and valence band is forbidden energy gap. Okay. Forbidden.
More than mobile electrons,
More the.
mobile free electrons. But since in d orbital,
I'm not speaking about the conductivity increasing or decreasing. I'm not speaking. I'm saying this is free. If this is free, the more electrons can come and sit right here. Okay. Comparatively to here, will be having more conductivity. Okay, I'm saying only because here in 3s and 3p, in terms of phosphorus, we have filled 8 electrons. Still 3 electrons is there. Can only occupy 3 electrons. But here in 3d, there is 5 orbitals and 10 electrons can accommodate, right? So comparatively, it will be more reactive. It is ready for bonding. In that terms, clear. So what happens? The distance between these two is forbidden energy. Now, I'm going to connect this thing with your semiconductors, insulators, and conductors. What will be the forbidden energy gap of your conductor? See, if this is your for conductors. This is your energy gap. This is your valence band. This is your conduction band. Okay, there will be no gap. The forbidden energy gap is negligible. So if it is negligible in the sense, If the electrons is present here, it can easily jump from here to here, right? Okay. So it can easily jump from here to here. Electrons can easily jump. Now, in terms of semiconductors, okay, in terms of semiconductors, what happened? There is valence band. Because there is valence band. Now, there is quite some gap between here. Clear? So, the two electrons, imagine there is 10 electrons. 10 electrons are traveling. See, this is valence band. In conductors, this is valence band, this is conduction band, means you can easily jump. Okay. If this is valence band and that is conduction, three people want to jump from here to here means only two probability can, only two people can accommodate. One people can't go, one people can go and come there. So all the electrons are traveling from valence band to conduction, and all the 10 electrons can't go and accommodate. 5 or 6 electrons can occupy, the remaining 4 can come down. So what happens here? Partial electrons can go. This is in semiconductors. Now in terms of insulators, your valence band will be here, conduction band will be here. Is it possible for electrons to jump from here to here? So it can't conduct it. Clear? Clear with this thing? Now you are getting to semiconductors. One more topic. So in terms, here we done theory. Now, in terms of semiconductors, you know semiconductors. Actually, have you studied about intrinsic semiconductor? I leave it. Okay. So here I have again. So in semiconductors, we know the gap is very less. Valence band, conduction band, the gap is very less. The probability majority is like around 5 to 6 electrons can jump from valence band to conduction. Okay. So when you're heating, what happens? Most of the electrons can go out. Okay. So what happened? What we are doing when we are just melting? Okay. So when you are melting, to increase the conductivity, we will go. That is, we will add the impurity. Okay. So based upon doping, the semiconductors divide into that is P type and N type. Okay. So based upon the semiconductor, based upon doping, the semiconductor is divided into two types. One is electron-rich semiconductor. Another one is electron-deficient semiconductor. Here, so now look at here, electron-rich semiconductor. Electron-rich in the sense the negative charge will be more, right? So that is N type. N means negative. N type semiconductor. This is P type semiconductor. Okay. Now we are going to see what is N type and P. Okay. So after this, the electrical properties is very 10 more minutes. I'll complete it. Okay. Are you okay with this thing? Or you want to leave? Huh? You have?
I should go for another.
Have to go for another class. Fine. So, huh? Sorry? You are also having another class. You have to share the finish for it. Okay, just wait for 5 minutes. I'll complete this thing and I'll go. It's fine. See, this N-type semiconductors, as I already said, electron-rich, which means electron-rich impurities should be added. Doping is nothing but adding the impurities, right? Electron-rich impurities should be added. Say, for example, group 14 element, you have to, when you need the electron-rich impurity, means you have to take group 15. Why you need to take group 15? Because in group 14, the valence electron is, in group 15, the valence electron is 5. Okay, so if I'm taking silicon, and in group 15, if I'm taking arsenic, okay, see, silicon will be having the 4 electrons like this, right? Okay, so when I'm doping, I'm adding arsenic here. Okay, this silicon by leaving, it will leave 4 holes. Here, it will leave 4 holes. So this arsenic will come here. This arsenic will come and oxidize. 14 is doped with group 13. Here in group 14 again I am taking in group 13 I am taking in terms of semiconductor gallium. Okay, so silicon, 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 silicon. Okay, now what happens? This when doping silicon will remove, and automatically what happens? The hole will be created. Now if I am placing gallium in boron group, there is gallium. Okay, boron, aluminium, gallium, indium, gallium. So what happens for gallium? There is only 3 valences. So 3 electrons will occupy the holes. So here what happened? The hole is free, right? So what happened? This electron will jump here, and here it will make the hole. This electron will jump here, and it will make a hole. So likewise, what happened? It will become an electron deficient. It will try to fill the hole. Okay, so that's why this was electron deficient semiconductor, P-type semiconductor. This is electron rich. Here, for electron rich, you need to dope group 14 with group 15. For electron deficient, you need to dope group 14 with
Group 10.
clear. Sorry, ma. For that, yeah, conductivity decrease. Because what happens is the electron will try to fill the holes. Okay, there will be no motion of free electrons from here to there. Okay, what happens? There is a hole, I will go and switch it. If there is a hole, I will go and switch it. The movement will be there, but not as fast as this. Clear? Yes, there is only one topic left. We can see tomorrow, but you can collect the assignments. Today, it's a 5 minutes topic. Just magnetic properties, just only for 5 minutes, I'll complete the chapter. Tomorrow we are getting into hierarchies and hierarchies. Right. Just take the assignment, okay? Don't ask. Assignment to your answer class almost 3 assignment thank you. Bye.